Hello, let's talk about sets. So here's a little glimpse of what you might need at some point about sets, but we just assume that you know all this. So set theory is a conceptual paradigm, and it helps understanding certain things and formalize them, and so allows to reason about them in a formal way, in a logical way. It can serve as a foundation in mathematics and in consequently in applications of mathematical reasoning in software engineering. It is attributed and has been basically invented by the gentleman on the left, Georg Cantor, and for a while it was a German kind of thing. So Karl Weierstrass on top, that's a PhD supervisor of Cantor, and Richard Dedekind is another scientist who contributed to that quite a lot. So what is it? It is about sets and its elements. So a set is some kind of collection of some kind of objects. The objects are distinct, so we don't need to talk about equality and equivalence and stuff like this. There is no order introduced, so we again do not need to talk about which element come first or last. It is just some volatile collection of some things. So, for example, this A is a set of numbers 1, 2, and 3. So here's how we write sets with curly brackets and with just comma-separated elements. Here's a special symbol for an empty set. So it could be written as on the right with curly open, curly close, but usually we use this special thing. Then if we write it like this, then we read it as X is an element of the set A. And of course, we could also write that X is not an element in the set A. And obviously, if there is some element in a set, then that set is not empty. So some examples, for example, we can see a programming language as a set. So in that case, it is a set of all valid programs, of all really texts of programs that you are allowed to write and you're allowed to execute. In that case, we can take some program and we say this is an element of a set which is a language. So this is a program in that language. It could also be a test set, and then a particular test case is a part of it. And A can also be a type. So types can be viewed differently, but with the set theory in mind, it is just a set of all possible values. So if you have an integer type, then it is a set of values from minus whatever, depends on how many bytes you have allocated for it, till plus something. So minus max int plus max int, something like this. And then x is a particular value of that type. So it's one of those numbers, and if it is an element in that set, then we can say this is a valid value of that type. We can also use this symbol to denote a subset of, so one set can be included in one of the sets. In this case, the smaller one is called a subset and the bigger one is called a superset. This line under the symbol signifies that they can be equal, so you can also have strict inclusion. This is a graphical representation of a subset. As an example, again, if we talk about languages, then suppose that A is a language, and then we have a new version of a language and it's backward compatible, which means that all programs that were valid in the previous version of a language are still valid. In this case, if we see again a language as a set of valid programs, then the old set, so the set of programs in the older version, is smaller and it is included in the current version. It could be subtyping, structural subtyping, in the sense that we're not talking about behaviors, we're not talking about which type is called by which name, but we are talking strictly about sets and elements that are allowed to be elements or members of those sets. And then again, it can be just a restricted version of a programming language which respects certain company coding standards, satisfies additional constraints. If you have additional constraints, then your set can only become smaller. Then we also have the union of sets, which is on the bottom there is a so-called Venn diagram where you have two sets, A on the left, B on the right, and then the union is all elements from A, all elements from B, all elements from both of them, but nothing beyond that. Then you have intersection of sets A and B, which is basically a selection of elements that belong both to A and B and nothing else. Then we have a difference. So a difference is all elements of A that do not occur in B. And then we have quite a lot of trivial properties, and this is not a complete list, but if you think about this, then an empty set is a subset of any set, because we can always say that any element of the empty set, of which there are no elements, so this already makes any statement about all these elements true. But we can say that all elements of an empty set also belong to a bigger set. Then we can also say that any set is a non-strict subset of itself. It is actually a very non-strict subset. It is equal to itself. But again, if we allow equality, then yes, it is a subset and a superset of itself. Then we have an intersection with an empty set, which is empty, because you intersect and you have to check that your that resulting elements occur both in your set and in an empty set, but nothing occurs in the empty set, so of course intersection is empty. A union results in the same set, so union with an empty something doesn't change the set. And then we have a difference with a disjoint sets. So disjoint means that their union is their intersection is empty. And if you do a difference, that means that you take all elements of one set and you check if they do not belong in the second set. But if you know that they do not belong anyway, then you have the same result. And all these things are very easily provable, and you can come up with quite a lot of other properties like this. Then we also have a complement. If we know kind of the set of all the elements, all the possible things that you have, then you can speak of a complement of a set, which is all elements that are in general considered. So in this universal set, sometimes it's written as I or you or something like this. The complement is basically all elements that do not occur in our set, but do occur somewhere. So we have some way of knowing them. And then finally we have, well, not finally, the second from last, we have a Cartesian product, which is a set of tuples, a set of pairs of elements, and in every pair, the first element belongs to A, the second element belongs to B. It's been introduced by René Descartes, also known as Renatus Cartesius. That's how he published, because publishing was done in Latin. So if you want to see this particular painting, you need to travel to the west of Amsterdam to a city called Haarlem, and there is a Frans Hals museum where this painting can be found. So examples of Cartesian product is coordinates, for example. If you're talking about a point with an x coordinate and a y coordinate, and this is basically an int times int type. Then 3D coordinates is of course int, int, int. If you have an address, it could be a string and an integer. And actually, Cartesian products are very useful to represent relations and functions, but that's for a different topic. Then we have a power set. So what is a power set? Sometimes it's displayed as 2 to the power of A, sometimes as this fancy P of A. A power set is a set of all possible subsets of A. And Georg Cantor proved a very nice theorem about cardinality, about how big the power set of particular set is. But here are some examples. So if we take an empty set, then the power set is already not empty. It is a set of one element which is empty. So in this case, empty is not only a subset of this power set, because as we said, an empty set is a subset of any set. But in this case, an empty set is the first and the only element of that power set. And then if you take a set with one element, then its power set consists of two elements. One of them is empty and another one is the set itself. And if we take all natural numbers, so all integer numbers from 1 till plus infinity, then we have also infinite power set, and that power set contains an empty set, a set that contains 1, a set that contains 1, 2, and any other set that contains any kind of combination of natural numbers. So a summary of this is that there is this thing called set theory. It is a powerful instrument. It has existed for at least 140 years in its formal form, in some kind of conceptual form, probably since the ancient Greeks. And it is suitable for many tasks. If you need to formalize something or prove certain properties, it is usually one of the first and the simplest instruments that you can pick up. And it basically boils down to thinking in terms of elements, subset, unions, etc. Thank you. That's it.